Hi everyone, this lesson is about Gaussian elimination, and for this lesson I'm going to be working through this using pencil and paper, or my OneNote screen instead of pencil and paper. So Gaussian elimination is a general method for solving systems of equations. Now, up until this point, you've probably solved systems of two equations in two unknowns, and what we're going to be doing now is looking at systems with more unknowns, and therefore more equations are needed. In this case, I have three pronumerals a, b, and c, all unknown values, and by the end of this we'll know what the values for a, b, and c are that solve each of these equations, all three of them. Now, the way to start this is to look at the coefficients of, say, pronumeral A or B or C, and pick ones that are fairly easy to work with. Now, in this case, they're all pretty easy. So for no particular reason, I'm going to focus my attention here on pronumeral B. That's not necessarily the only choice. I could have worked with variable A or variable C, but I'm going to try and eliminate variable B. Now, to do this, I don't try to do all three at once. I'll try to do just two equations. So looking at equation 1, I note that the pronumeral here is positive 2, and in equation 2, it's negative 1. They don't exactly match. I would need to double the size of this second value in order to make it equal and opposite. And that's exactly what I'm going to do. I'm going to start off by writing 2 times equation 2. So I double everything. So instead of 2a, it starts with 4a. Instead of minus b, it's minus 2b. Instead of plus c, I'll have plus 2 lots of c. And instead of equals 3, I'll have equals 6. That is literally just a multiple 2 times. Now, equation 1, on the other hand, it doesn't need any changes. If I write equation number 1, so just good old, if you want me to write 1 multiplied by, I can do that, but it's just plain old equation 1. Here we go, a plus 2b minus c equals 2. So importantly, the pronumeral b is now a negative 2 in the first and a positive 2 in, they're equal and opposite. That's what I was trying to go for here. So if I add these two equations, 4a plus a is 5a. The b's cancel as I wanted. 2c takes c is plus c equals 8. Now that is a combination, a linear combination of equation 1 and equation 2. I've managed to get rid of pronumeral b. I will refer to this as equation 4. It's something quite new. Now, I need to do this a second time using a different pair of equations, but importantly, I'm still going to try and eliminate pronumeral b. So this time I might focus on equation 2 and 3. I notice that pronumeral b, they are already equal and opposite. So if I move to the side, I could literally just have 1 times equation 2 and 1 times equation 3. So before I lose it, equation 2 was 2a take b plus c equals 3. And equation 3 was also 2a, this time plus b plus 3c equals 13. So I'll add those two now. So 2a plus 2a gives me 4a. As I said a moment ago, I selected them on purpose because conveniently pronumeral b were already equal and opposite. C plus 3c gives me 4c equals 16. Now I could work with that, although I can see straight away that each of those divides nicely by 4. So let's divide through by 4. So we've got something easier to work with. There we go, and I will call that equation 5. So you can see what's happened. I've started with a system of 3 equations in 3 unknowns, and by selecting 2 of the equations, I've managed to eliminate pronumeral b. And then by selecting a different pair of the original equations, I again eliminate pronumeral b. It's important that we eliminate the same one because now my new equations here, 4 and 5, they only have pronumerals a and c. Now I'm going to do the same process again to eliminate one. I'll look carefully at what I've got to work with. I have 5a over here plus a positive c, and then I have a single a and a positive c. Well, I think I could go 1 times equation 4, literally just the original 5a plus c equals 8. And now I could go negative 1 by equation 5. So that's a negative a subtract c equals negative 4. Sometimes multiplying by negative 1 is a handy thing, a trick. So we got here at 4a. Now, as I was trying to, I've managed to have equal and opposite amounts of pronumeral c. They eliminate, they disappear. And 8 plus negative 4 is 4. Immediately we would have that a equals 1. Now we solve by back substitution. Look back at equation 4 and equation 5. Equation 5 looks a bit easier, so I'll work from there. And I'll just make a quick note from equation 5. Now I could see from equation 5 here that c would equal 4 take a. So let's make a note. C equals 4 take away a. Well, we know that a is 1, so c equals 3. We've just solved for c. Now we've got a and we've got c. In order to calculate b, we'll have to go back to one of our originals. Again, you can pick any one you like, but make a choice that's nice. I might choose equation 3 because I just have positive b sitting right there already. I'd just have to transpose the 2a and the 3c. So let's write that. From equation 3, b would equal 13. Now if we go back, I'd have to subtract 2a, subtract 3c, subtract 2a, subtract 3c. Now a equaled 1, so that's subtract 2. C equaled 3, that's subtract 9. 13 take 2 is 11. 11 take 9 is 2. So we've got our solutions there. I'll make a little note over at the side here. A equals 1, B equaled 2, C equaled 3. That's the unique solution to the three equations that we started with. Importantly, the method we've used here today is called Gaussian elimination. We eliminate variables. Now, you've used elimination method when you did 2 by 2 equations. We just have to be a little bit more methodical about it when we have systems with more variables. So that's a nice little introduction, I hope. Obviously, it gets a bit more tedious if you have 4 equations and 4 unknowns and so forth. It can still be done. You have to be very methodical though. So the process just will take a lot longer. Now, I do want to have a little bit of a discussion here while we're here about, go back here to a 2 by 2 system for a moment, and you would have seen this in prior learning, how we can use, in a 2 by 2 case, we can use a graph to represent these linear equations. So my first one, 4x plus y equals 9, that's equation number 1 here. And then equation 2, negative x plus 3y equals 1, that's this one over here. Now I'm sure you would be familiar with the fact that we could solve those two by Gaussian elimination, and we would come up with the solution that matches the intersection point of these lines here. So x would equal 2 and y would equal 1, just like the computer has shown us. Now that's lovely, and that's a little bit like the two-dimensional version of what I just did in 3 dimensions. And I got a unique solution. So when we get a unique solution to these things, we say that these equations are, now I've got to get the right word here, they are consistent. Consistent equations have a solution, have a unique solution. Now, let's just let's just do something to our equations for a minute up here. What if I go to this equation and what if I made that, say 4? I can do that. And what if I take away that 3 there? So that's just 4x plus y equals 1. Now, when I do that, I end up with two parallel lines. So you can see here that the intersection point is now doesn't solve, it doesn't work. If I tried Gaussian elimination with this, I would end up with an impossibility. I would end up with something like 0 equaled 8. Now that's obviously wrong, and it means that these equations are inconsistent. They have no solution. And in the two-dimensional case, inconsistent equations produce parallel lines. Now there's a third possibility. Um, my equations, what if I do something like this? What if I make that one 8? And what if I make the coefficient there 2? And what if I make that 18? Now, before I hit enter, you'll probably note that double that is 8, double 1 is 2, and double 9 is 18. And what do I end up with? Again, I end up with uh, no solution, no unique solution, because both of these lines, if I turn off equation 1 and then put equation 2, do you see that they're pretty much, they are the same line? One equation 1 multiplied by 2 gives me equation 2. So these are not independent equations. Because they're not independent equations, they're really the same thing. I could just divide equation 2 through by 2 and I end up with having, I've got exactly the same equation sitting there. Now this is a pretty obvious example of a dependent system. So a dependent system like this doesn't have a unique solution. Effectively, any point that solves equation 1 also solves equation 2. It's not that there's no solution, it's just that there's an infinite number, so it's not a unique solution. That's when you get multiples. Now, oh yeah, I don't need to save that. Now, if I come back to this example for a minute, sometimes you can have dependent equations in the 3x3 system, which are a little bit harder to spot. For example, just imagine that I wanted to, instead of equation 3, pretend equation 3 is no longer there, but instead I give you the following equation to work with as equation 3. What if I give you 3a plus b equals 5? Now that looks like a different equation to equation 1 or equation 2, but in fact it is a dependent equation because this is really just equation 1 plus equation 2. I added equation 1 and 2 in my head and wrote that down pretending that it was going to be a third equation for the system to work with, but it's not. It's not really any new information. So if I tried solving original equation 1 and 2 and this new one, I would not get a unique solution because they're not an independent system of equations. Okay, that's enough for this first introductory go. Thanks for watching. I'll see you next time.